All right, we're continuing with chapter 4, which is on the graphs of the trig functions. We just finished sections 4.1 and 4.2, which was all about the sinusoids, so the graphs of sine and cosine. In this video, we're going to go through section 4.3, which is on the graphs of tangent and cotangent. So previously, we've gone through the domain and range of tangent and cotangent. Let's go through that again to get a sense of what we expect the graphs of tangent and cotangent to look like. All right, so we could use the unit circle for the definition of the trig functions, but I like using the general definition just because that's the most fundamental definition of the trig functions. So x, y, we've got the initial side here and the terminal side. I'll just draw in any arbitrary location. And I like to make the terminal side noticeably different in length than the initial side, just to indicate that the length, these lengths don't matter. Okay, and this terminal side defines an angle, theta, measured from standard position. So that's, we want to evaluate the trig functions of this angle. Now we pick any point along this terminal side, doesn't matter where it is, and then we make a perpendicular from this point to the horizontal. And that creates a right triangle with hypotenuse r and side lengths given by the coordinates of this point here, which in this case, x is going to be negative and y is going to be negative. In the first quadrant, both x and y would be positive. In the second quadrant, x would be negative, y would be positive, etc. Okay, and so with this notation here, you can write out the definitions of the trig functions. Sine is y over r, cosine is x over r, etc. So we're thinking about that tangent theta is y over x. Yeah, you do. So there's the reference angle here, and you do SOHCAHTOA based on the reference angle, just honoring the signs of the x and y. You're not finding the trig functions of the reference angle, but you're just using that angle to do SOHCAHTOA, again honoring the signs of x and y. That's the definition of the trig functions. So tangent theta is, you come here, you do opposite over adjacent. There'd be negative, the y would be negative, the x would be negative. And then cotangent is just the reciprocal of tangent, so x over y. Okay, so when we're thinking about the graph of tangent and cotangent, so what we're thinking about is, like this is theta, the independent variable, and then the y is tangent theta and cotangent theta. So when theta is equal to 0, the triangle has like collapsed, is how we think about it. Well, the y is 0. When theta is 0, the y side of the triangle is 0, and the x is equal to r, positive r. Okay, so when y is 0 and x is non-zero, that means tangent theta is 0, but cotangent theta doesn't exist. Now, because you're dividing by 0, however, we can think about, though, that x is, equal to r, y is 0, so that's in infinity. And from algebra, we know that that's a vertical asymptote. A finite number divided by 0, it's not but like if it's when you get really, you never, it doesn't exist. Cotangent doesn't exist when theta is equal to 0, but when theta is close to 0, it's a vertical asymptote behavior. So that's interesting, and if we think about whenever theta gets really close to 90 or pi over 2, yeah, let's think about it in radians. When theta gets close to pi over 2, you're going to have the x is going to be going to 0 and the y is going to be approaching r. So this is approaching infinity as well. So this, which is what we expect, cotangent and tangent are going to be very similar. this is going to have a vertical asymptote as well. So that's interesting. So cotangent and tangent have vertical asymptotes. Now, we know that they're going to be periodic because every trig function, based on the definition of trig functions, is going to be periodic, because we know at the very least it's going to repeat every 2 pi, 100%, right? But there's the potential, though, that maybe the period is less than 2 pi with certain trig functions, okay? But, all right, let's come back to tangent. So we start at theta is equal to 0, tangent at theta is 0, and then it goes, as you're increasing theta towards pi over 2, what's happening? Well, the x is getting smaller and the y is approaching r. And so really what it's doing is it's going from 0 to infinity. It starts at 0, then it just increases until you get really close to pi over 2, and it's like infinitely large, and then you get to pi over 2, and then it doesn't exist. That's a vertical asymptote. So it's like, if this is pi over 2, it's doing something like, this is a vertical asymptote. It just does something like this. Okay, let me extend this. Now, when you cross over, what happens? When you cross over pi over 2, what happens with tangent? Well, then all of a sudden, you've got the y is equal to r, and x is really small, like right when you cross over, but x is negative now. So you've got like a positive, just positive r, and then a tiny, tiny negative number right when you cross over the vertical. So that's going to be the vertical asymptote, but in the negative direction. And then as you go past pi over 2 towards pi, eventually you're getting to where the y goes to 0 again, and the x is negative r, but that's still 0. So it goes back. It just does this. It's just the same behavior, but it's like this. Exact same shape, but like that, right? Now, when you keep going past pi, let's see, the y and the x are negative, so it's positive, which makes sense. We're going to continue past into the positive region until you get to theta is equal to, when you're approaching theta is equal to 3 pi over 2, y is approaching r, but y is going to be negative. So kind of like negative r. Yeah, y is approaching negative r. And x is approaching 0, but from the negative direction, so it's going to be going to positive infinity. So yeah, 3 pi over 2 is going to be another vertical asymptote. So something like that. Okay, now when you cross over, you're going to have a negative, a really close to negative r for y, and divided by a tiny positive number. So that's going to be approaching the negative infinity. So, and then as you go towards 2 pi, it's going to go back to 0. So, okay. If we look at this, we can see the period. It's going to be like this, repeating over and over again, this pattern here. And so this is 3 pi over 2. 3 pi over 2 minus pi over 2 is pi. So the period is going to be pi, right? We repeat this pattern every pi, okay? And cotangent, we expect it's going to be very, very similar to this. Just it's going to be the exact same thing, just kind of, like a mirror flip or something, just because it's the reciprocal, right? It's the exact same behavior, except at the horizontal you have the asymptote behavior, and at the vertical it goes to 0. Same exact behavior, though. Okay, so let's get into this section and take a look. Okay, graph of the tangent function. Consider the table of selected points accompanying the graph of the tangent function. On the next page, these points include special values between minus pi over 2 and pi over 2. So that's going from the vertical to the negative. Those points are going from here to here. And why are they plotting those points? Well, that's the period, right? Going from the right side of, this is where you're going from negative infinity all the way through 0 to positive infinity, and then it crosses over the vertical asymptote and repeats. So like that. So like that's the periodic nature of tangent. It's like it goes from here to here with a continuous curve. Then you cross over the asymptote. Then it repeats that same pattern again, over and over again. So it's like the period is pi in the sense of going from vertical to vertical. Okay. Yeah. So it has the vertical asymptotes. Yeah, we know what a vertical asymptote is from algebra. It's a vertical line that the graph approaches but does not intersect, right? As you get really close to a finite number in the numerator, and you're getting really close to where you have something that's extremely almost zero in the denominator, then it's like approaching infinity, right? We go into detail about vertical asymptotes in algebra with like rational functions, rational expressions. So go check that out if you need. Okay, so yeah, as the x values get closer and closer to the line, the function values increase or decrease without bound. That's right. So like you could technically create, when you could create when tangent goes from, goes from here to here, so negative infinity to infinity, literally you can create any number you could possibly imagine with the tangent function going, over a period. You just have to, divide by it, take the value that's close to the radius, the finite value in the numerator, and divide by whatever you want. You could get as big of a number as you want, right? The range of the tangent function is negative infinity to infinity. Unlike the sinusoids, it was just minus 1 to 1, right? But the domain isn't going to be negative infinity to infinity because it's you can't divide by 0 at some points. Whereas the domain of the sinusoids was all real numbers. Okay, now if you plug in, if you check for symmetry of the tangent function, you'll see that it's an odd function. So tangent of minus x is equal to minus tangent of x. So it's symmetric about the origin. The graph of the tangent function is symmetric with respect to the origin. Okay, and we're going to see that cotangent is also an odd function. All right, so if we come here, yeah, this is a period is going from, you can think about from the negative pi over 2 to pi over 2, the negative vertical to the vertical. That's like a continuous period. And then you come to this side and you're like starting up here. When you go from here to here, it's like you're doing this. Okay, but you can see it's odd in that if you take any point on the graph, x, y, and multiply the x by -1 and the y by -1, so flip here, you're on the graph. And it's the same idea if you would have, if you drew, this is universal for the entire tangent function. So if you did this, and then this, you take a point here and you go minus x minus y. So you flip here and then you flip here and you're on the graph, right? We flipped about the y, we went all the way over here. So it's an odd function. And the tangent function has period pi. Not 2 pi like the sinusoids, period pi. Because tangent x is sine x over cosine x, tangent values are 0 when sine values are 0 and are undefined when cosine values are 0. Right, as x values increase from minus pi over 2 to pi over 2, tangent values range from minus infinity to infinity and increase throughout the interval. The same values are repeated as x increases from pi over 2 to 3 pi over 2, from 3 pi over 2 to 4 pi over 2, etc. So yeah, the domain of the tangent function is going to be, well, let's start with the range. The range is negative infinity to infinity. Okay, and then the domain is any vertical quadrantal angle. So pi over 2, 3 pi over 2, or any angle coterminal with pi over 2 or 3 pi over 2, right? So whatever this angle is, I think I said 5 pi over 2, or no, 2 pi plus pi over 2 would be 4 pi over 2 plus pi over 2. So yeah, that's 5 pi over 2. Right, so any of any vertical angle, which is pi over 2, 3 pi over 2, or any angle coterminal with that, it's undefined. That's the vertical asymptote points for tangent. And then any angle that's horizontal, so like 0 or pi or anything coterminal with 0 or pi is a x-intercept of tangent. This is just we're just talking about tangent at the moment. Okay, so let's see. I think we just covered everything. The domain, they write it this way. It's pi over 2, 2n plus 1 times pi over 2, where n is any integer, covers all the vertical angles that you can't input into the tangent function, and then the range negative infinity to infinity. The graph is discontinuous at values of x. Yeah, that's the vertical asymptotes. X-intercepts in pi, period pi. There are no minimum or maximum values, so its graph has no amplitude. Yeah, there's no, with sine and cosine, we had these kind of points, right? Well, there's nothing like that with tangent. And the graph is an odd function. So that covers everything. Now, as you can imagine, cotangent is going to be very similar, but there's some subtle differences. So let's take a look. A similar analysis for selected points between 0 and pi. Yeah, so we're going to go with cotangent. We're going to be looking at, it's going to be continuous coming from 0 to pi, and then from pi to 2 pi, because it's going to be undefined at the horizontal. Okay, it's an odd function. Okay, so let's see. There's cotangent, and so it doesn't cross through the x is equal to 0, right? And so it has period pi, and tangent was like, you went from negative pi over 2 to pi over 2, and you did like that. And that just repeated to the left and to the right. Cotangent is you can do, we saw 0 to pi, okay, 0 to pi, and it's like flipped about it, and if there's like an imaginary vertical axis here at the center of this interval, it's like a mirror flip of cotangent about this axis. So it's doing this. And that's going to repeat everywhere. And so you can see it's odd because you can take this point, flip about the x, flip about the y, you're on the graph. Right? And you can see how the period is pi. That makes sense. The period's going to be pi. And it makes sense that it's shifted. It's shifted. It's kind of like it's shifted pi over 2 from tangent, because tangent, like the base period goes from here to here, but cotangent, the base period goes from here to here, so they start pi over 2 apart. It's kind of like, you can think about it kind of like a phase shift of pi over 2, but it's not the same function. So, but you can kind of think of it that way. If they're shifted pi over 2 apart. The tangent starts here, cotangent starts here. Okay, so let's see. Period pi, cotangent values are 0 when cosine values are 0, and then when sine values are 0, they're undefined. Range negative infinity to infinity, and then, yeah, the x-intercepts for tangent are the vertical asymptotes for cotangent, and vice versa. The x-intercepts for cotangent are the vertical asymptotes for tangent. Okay, no minimum or maximum values, symmetric respect to the origin. So yeah, there you go. Now it says the tangent function can be graphed directly with a graphing calculator using the tangent key. To graph the cotangent function, however, we must use one of the identities, these identities, because graphing calculators generally do not have cotangent keys. So yeah, this book is this is not up to date, because graphing calculators or just softwares online, whatever, can easily, you can just type in cotangent, right? I got all the trig functions here. I can put this directly into the, so there you go. There's cotangent. All right, so we're going to sketch tangent and cotangent. So let's see the guidelines they give to make this as simple as possible. So step 1, determine the period. So the period could be adjusted, right, by scaling about the x-axis. To locate two adjacent vertical asymptotes, solve the following equations for x. So yeah, solve for when the argument is equal to whatever period you're sketching with, which, I guess typically would be the minus pi over 2 to pi over 2 for tangent and 0 to pi for cotangent. Just set the argument, whatever it is, equal to those values to get the x values that correspond to the vertical asymptotes. Then sketch the vertical asymptotes. So you want to get 2 of them, right? Because you're going to know that's going to be the start point and the end point of the period. So, we might even have a shifting about the x-axis. So we can put it into that form where we've got, some factor, let's say b, and then x plus or minus some number. And so we can see the shifting here, and then we can see the scaling here. And so with that, we can find the 2 vertical asymptotes, which would usually correspond to wherever the minus pi over 2 and the pi over 2 have been shifted. Well, right, depending on how the period has changed, we can, similar to what we did with the sinusoids, we can just find based on the change in period and the shifting, where's like the quote unquote new minus pi over 2 and pi over 2 for tangent, or the new 0 and pi for cotangent. And then we'll draw the vertical asymptotes at those spots. So you sketch the vertical asymptotes, then divide the interval form of that vertical asymptotes into 4 equal parts. Okay, so 4 equal parts. Interesting. Why are they saying that? I guess to help you sketch it. So, because to me, you don't even need to divide it, because the midpoint of that between the vertical asymptotes is going to be the x-intercept, and then you have everything you need. But I guess it's a good idea to plot a few points to help to guide you with the shape of the curve. Evaluate the function for the first quarter point, the midpoint, and the third quarter point. Well, shouldn't the midpoint be? The midpoint should be the x-intercept for tangent or cotangent. I wonder why they're not saying that. Yeah, it definitely should be, because you've got your vertical asymptotes drawn, right? That for tangent, that's like the 2 verticals, and for cotangent, it's the 2 horizontals. So when you're halfway between the asymptotes, you're at 0. So yeah, it's going to be 0 at the midpoint. So they're saying evaluate the quarter points too, just to help you with the shape of the curve, and then join the points with a smooth curve approaching the vertical asymptotes. Indicate additional asymptotes and periods of the graph as necessary. Oh yeah, so right, we'll copy and paste like we did the period with the asymptotes up and down the curve once we've drawn one period. So yeah. So, okay, y is equal to tangent 2x. So that means that you've shrunk about the y-axis by a factor of 2. So the period has gone from pi to pi over 2. But there's no horizontal translation. So you're going to have, it's going to be like this. Instead of pi over 2 or minus pi over 2 to pi over 2, it's going to be minus pi over 4 to pi over 4. And then you're going to plot, the midpoint's going to be here. You'll plot a point here, and it's going to look like that. And then just copy and paste this all the way down the curve. And we're going to work examples to where you can get a feel for the mechanics of this. But yeah, you see minus pi over 4 to pi over 4. And they plot a couple of points. Okay, let's see. Minus 3 tangent 1/2 x, so scaled about the x-axis by a factor of 2. So you're going to go from period pi to period 2 pi. So it'll go from like minus pi to pi, right? Then at the midpoint, it's going to go through the origin, no shifting horizontally. And then it's scaled up by 3 with the y-axis and then flipped about the x-axis. So instead of being like this, it's going to be like this, which is kind of like the cotangent curve. So yeah, that's because yeah, that makes sense. You could flip about the x or y and get the cotangent curve because they're both odd functions. You flip about the x and then the y, or the y then the x, and you get the original curve, right? So, okay, yeah, we're going to get it. It's going to look like that, but with the stretching, it's going to stretch it out. So it's going to be more stretched vertically. So that's why you plot some points and, you know, I don't know. So maybe it'll be kind of like that, just more stretched vertically. Yeah, you plot some points to guide you on the shape. Okay, let's see. So yeah, this is cotangent, and same idea, but we're going to be adjusting the period is cut in half here. So you go from 0 to pi to 0 to pi over 2. And then 1/2 means it's kind of scaled down, so it's going to be scrunched a little bit. I didn't draw it right. You see how it's kind of scrunched? It's kind of pushed in from the top and bottom. Okay, then this has been shifted vertically, and to apply vertical shift, yeah, I mean, you could kind of imagine a new horizontal axis, right? And you just do this, and then that's it. You draw the exact same curve with everything that we just talked about, but it's like been shifted up. It's like the x-axis has been shifted up, so you just go from there. And again, we'll work a bunch of examples. Here they have a horizontal shift, and so all you're going to do here, so this is cotangent, you're going to identify so there's been no scaling about the x, but so we would normally sketch from 0 to pi over 2. But since it's been shifted to the right, pi over 4, now we're going to be sketching from pi over 4 we would sketch from 0 to pi normally. Now with the shifting, we're going to sketch from pi over 4 to pi over 4 plus pi, which is what? Pi over 4 plus 4 pi over 4 is 5 pi over 4. So pi over 4, 5 pi over 4. The midpoint's going to be it's going to cross the x-axis, and then it's been flipped minus cotangent. It's been flipped about the x-axis, so it's going to be like this kind of shape. There's no scaling about the y, but it's been shifted down too. So it's going to be, 1, 2. This is going to be like the new horizontal axis. So like that. Let's see. Yeah. And again, we're gonna work a bunch of examples, so you'll get a good feel for this in the next video. Okay, connecting graphs with equations. So here we're given a graph, and we want to determine the equation. So let's see. We've got, this looks like this could be, all right, minus pi over 2 to pi over 2. That's, I think tangent, right? But then tangent's like this. So maybe this is like a minus tangent, or it could be a cotangent shifted, because tangent and cotangent have the same period, right? Okay, but then they say x is equal to pi minus pi over 4. The graph is equal to 2, so you can figure out that it's been scaled up by 2, and then it's tangent, but it's been flipped. So y is equal to minus 2 tangent x. Here, this looks like a 0 to pi over 2, that's like, you think cotangent, and it has the right shape. Shifted down, and then you could tell somehow they can tell the scaling here. Let's see. So yeah, they could just tell when they give you points, and so you could use those points. You can see what the x is and what the y is, and so with those points you can figure out how it's been stretched. If you know we can tell by looking at this that this is cotangent, unshifted horizontally, not flipped, shifted down -1. So now just use the points to see how it's scaled vertically, and you can get the equation. Okay, but yeah, now it says because the trig functions are periodic, there are infinitely many equations that correspond to each graph in this example. Yeah, because this could have been a shifted cotangent, horizontally shifted, right? So we could have said -1 minus cotangent minus 2x. We could have written that as a shifted tangent, or vice versa. This could have been tangent flipped and then shifted, right? But it says when writing which equation do you use? It says when writing the equation from a graph, it's practical to write the simplest form. So yeah, you'd like to, if you could have an argument without any shift, with no shifting, that'd be nice, right? And then no flipping, I guess, just as simple as possible. Okay, let's work some example problems.